Hello, welcome to this class of digital electronics. Today, in short time, we shall try to understand another flip-flop called JK flip-flop. JK flip-flop. We have already studied about this SR flip-flop, then D flip-flop, and now we are going to study about JK flip-flop. In SR flip-flop, we have seen that when S and R both are 1-1, then the output was indeterminate state, means not clear condition, means we were not sure what shall be the output, whether it be logic 0 or logic 1. So in order to avoid that, we reached to this D flip-flop, in which the condition of 1-1 to both the inputs of cross-coupled NAND gate was avoided. But suppose if we want to keep two inputs, as well as we want to avoid this indeterminate state. The solution is JK flip-flop. So let us see the circuit diagram of JK flip-flop. So JK flip-flop is a cross-coupled again, the way it was there for SR flip-flop. So we draw like this. Output of first NAND gate is given to input of second NAND gate is connected to the output of first NAND gate, second NAND gate, and then this input is connected to the output of this NAND gate. Same here. We are just following the way we have drawn the circuit diagram for SR flip-flop. Now, only the difference is that there is a feedback. Let us see how this feedback. So this is cross. So first, the input of first, suppose upon output of this NAND gate, you know what? Similarly, the output of this NAND gate is connected to the input of this NAND gate. So in this way, it is a feedback, cross feedback. And now we can give one more input, J and K. So this is the circuit diagram of JK flip-flop. Here QT and QT bar, two outputs. So this is JK flip-flop. So I will give just number so that when we are talking about, we should understand this is gate number 1. So this is 2, this is 3, this is 4. So this is 3 input NAND gate, 1 and 2. Number 3 and number 4 are as usual 2 input NAND gate. So let us try to write here. It's to functional table. Functional table. So functional table tells like this. We have here the previous output QT, we have J, we have K. So now we can write here next output, that is the QT plus 1. Since it has 3 bit input, this is input and this is output, so we can write 3 bit number configuration or all possible combination of 3 bit number. So I will write here, so 0 0 0, then 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Let us see by writing in decimal number whether all are okay or not. From 0 to 7, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. So all numbers are in order. So I will not consider all cases. You can verify. I will take suppose first. I will write here the output and then you can verify. So this will be 0 0 1 1. That here P bar, that will be 1 0 1 0. So here for first 4, J is followed from here. First 4 and rest 4 K bar, J and K bar. So that is why the characteristic equation is J QT bar plus K bar QT. So from there we can see first 4 inputs or first 4 output, that is QT plus 1, is nothing but J. It follows J. So whatever J value is there, 0 0 0 0 1 1 1 1. So you can see all 4 inputs of J is just replicated in terms of the output. And now rest 4 is K bar. So K is suppose 0, the output is 1. K is 1, output is 0. K is 0, output is 1. K is 1, output is 0. So one input I would like to just verify. Suppose I want to verify the state here. Suppose J and K both are 1, 1. Okay. This state I want to verify, right? This one. So that you can see, as I was telling S and R both are 1, 1, that we were not able to determine what shall be the output. So I'm taking here, suppose J and K both are 1, 1. Suppose J and K both are 1, 1. And QT at that time here, suppose this is 0. So what shall be the QT plus 1? Next one. So if this is 0, so obviously it will be 1. And here clock pulse is 1. Logic 1 has come. And now try to get whether the output is this one or not. So let me analyze using another thread. Yeah. So here we can see this is here, this is the output 0. So 0 is coming here, 1 is here, and 1 is here. So any 0 makes output 1. This is logic 1. Okay, not up to point, let me use blank only. So this is 1. And here you can see this is logic 1, QT is 1. So 1 is coming here, 1 J is equal to 1, and clock is 1. So output will be 0 here. That gate number 1 will be output 0. So the output of this gate 3 is nothing but logic 1, because any input 0 gets output 1. So you can see this state is simply 1. So you just see here next state, that the next output is 1 when both J and K are 1, 1, and previous output was 0. If previous output is 1, so it will be 0. That can also be verified. So this way we can understand the function of JK flip-flop, keeping 2 inputs and avoiding the condition of indeterminate state in the state which were found in the SR flip-flop. So keeping 2 inputs. So this is JK flip-flop. There is another problem that is called race around condition that we will discuss in next class. Race around condition in JK flip-flop. So I hope you could understand. You can the way we have derived this characteristic equation using Karnaugh, you can also find out this characteristic equation in case of JK flip-flop by using this functional table. From here, we shall able to write the excitation table also. So that also I think we should take up in next class. Thank you for attending this.